We're dealing with two major factors that prevent us from accurately solving the scene: an unknown focal length and strong lens distortion. That said, our 2D trackers are generally stable and cover the whole shot, and we can always add more if needed. Now the main point, the scene is distorted, but all the geometry is straight. We're solving the camera, assuming, say, the wall is flat. So if we ignore the distortion, the solver receives incorrect coordinates and the tracking will be inaccurate. What can we do? Let's start with a simple distortion model, for example the classic one. We'll switch to lineup mode, and already at this stage, by adjusting the distortion value, we can see which way the image bends. Of course, eyeballing it isn't the most accurate approach, but at this point, it's a decent starting point. Let's start by adjusting the focal length and then move on to distortion. So the focal length is unknown, but we should at least estimate the range it's likely to fall within. We know the wider the field of view, the shorter the focal length. For example, on a DSLR with a 36 by 24 mm sensor, ultra-wide lenses are typically around 5 to 8 mm. Here the sensor is much smaller, only 6 mm wide, and the field of view is obviously extremely wide, so we can safely assume that the focal length is somewhere between 1 mm and 8 mm, maybe even shorter. Even if the exact number isn't listed anywhere, it's important to roughly estimate the range so we're not guessing blindly. Now let's use the adjust function. That means the parameter will be optimized automatically. Open parameter adjustment window. One of the most powerful tools in 3DEqualizer. Here we can add any parameter for automated tuning. Right now, focal length is already selected. You can also add other parameters if needed. We tell the software the range it's allowed to search within, and it tries different values, checking which ones produce the lowest error in the solve. This way, we can quickly get an optimal focal length, even without exact data, as long as we provide a reasonable range. But right away, it's important to understand this. Adjusting multiple parameters at the same time can take a long time. Think about it. If you're adjusting one parameter across a range of 1 to 10, the software checks 10 values. If you're adjusting 2, it's 10 times 10 equals 100 combinations. 3 parameters, 1000 combinations. And the more parameters you add, the number of combinations grows exponentially. That's why it's smart to start with just one parameter. Right now, let's focus on understanding how the parameter adjustment window works. For now, we'll remove any extra parameters and keep it simple. At the top of the window, you'll see a graph. This shows the values the software is testing during adjustment. So if you define a range from 2 to 8 mm, each tested value will appear on the graph, and you'll be able to visually see where the lowest error occurs. Below the graph is a list of adjustable parameters. Each one has a checkbox labeled Adjust. This enables or disables it for optimization. If you've added multiple parameters, you can temporarily disable one without removing it. Just uncheck the box. But keep in mind, if none of the parameters have the adjust box checked, nothing will be calculated. So, for now, let's leave just one parameter, the focal length. Check its adjust box and define the range we want it to search within. The visualize checkbox means we want to see the parameter adjustment process plotted on the graph. This is really helpful. Even when we're adjusting values blindly, the curve on the graph helps us understand whether the optimization is heading in the right direction. Range defines the span of values to test. In our case, that's for the focal length. Fine is the standard or medium range. For example, if your current focal length is 30 mm, fine will search from 27 mm to 33 mm. You can widen or narrow this range based on the current value, or manually set it using the custom option. Wide gives you a large range, like 5 mm to 100 mm. That's helpful when you have no idea at all what the correct value might be. But this kind of range is more suitable for full-frame sensors, where focal lengths commonly fall into that bracket. For our case, with a small sensor and strong distortion, that kind of wide range is unnecessary and excessive. Let's try it. As I mentioned earlier, the focal length here is unlikely to be above 8 mm. Brute force is a method where the software tests values sequentially without any optimization heuristics. If you set 20 samples, the selected range, in this case from 1 mm to 8 mm, will be evenly divided into 20 steps, and each value will be tested one by one. For example, if we set just 8 samples, to make it easier to demonstrate, and hit adjust, the software will try from 1 mm to 8 mm, making 8 separate calculations, one for each sample. If I set, for example, 80 samples, the software will test values in 0.1 mm increments, 1.0, 1.1, 1.2, and so on, up to 8 mm. That means it will make 80 evaluation attempts across the specified range. Brute force is a straightforward method. It simply tests every value between the minimum and maximum, distributed evenly according to the number of steps you've set. Adaptive, on the other hand, works differently. The software might start by comparing, say, 3 mm and 6 mm. and see which one produces a lower error. If 3 mm is better, it then tests 2 mm and 4 mm. If 2 mm wins, it tries 1.5 and 2.5, and so on. This is an iterative narrowing process. Instead of checking every possible value, it focuses only on the areas that make sense, refining the estimate step by step until the optimal result is found. Let's choose brute force, especially since we're only adjusting a single parameter. We'll leave the sample count at 20. The remove button removes a parameter from the adjustment list. Advanced options let you specify which shot and point group the adjustment applies to. In our case, it's simple. One shot, one group, so we don't need to change anything. If we had a lens that wasn't part of a certain group, we could exclude it from the solve. Or conversely, we could ignore a group that we don't want to affect the results. Brute force all and adaptive all will switch all parameters in the list to that mode of adjustment. These arrow buttons next to each parameter just expand or contract the search range. Remove all clears the entire parameter list. Click adjust and let's see what we get. The parameter adjustment is complete, and the program now asks whether to apply the best result from the sample set to the project. The best result has an error of 1 pixel, which is generally a good outcome. We can see the tested values. For example, 7.97 was one of them, and 1.03 turned out to be the most accurate. Looking at the graph, we noticed that the best point isn't in the center, but rather near one of the edges. If the curve drops sharply and the minimum isn't centered, that usually means it's worth refining the search further in the same direction, where the error continues to decrease. The vertical axis represents solve error, and the lowest point on the curve indicates the best result. Let's run the adjustment again, but this time, set the range from 5 to 3 mm. What's throwing the solver off, despite the low error value, is the extremely strong lens distortion, which we're currently not accounting for at all. But let's take a look at what we get anyway. We can see that the minimum value has hit the edge of the selected range, and based on the graph, it clearly doesn't belong there. So we'll extend the range in the direction where the error keeps decreasing and run the adjustment again. The error got even lower. Let's check the result. The solver determined that the lowest error occurs at a focal length of 0.89 mm. This isn't a boundary value, meaning it didn't land on either edge of the range. Let's see how the solver handles the camera with that focal length. Though once again, it's worth pointing out, starting with focal length adjustment in a shot like this isn't ideal because the distortion here is really strong. If the shot has only minor distortion, it usually makes sense to start by adjusting the focal length. In our case though, the distortion is quite severe, so it's more appropriate to solve both focal length and distortion together. But we'll get to that in the next step. For now, the selected value has already been transferred to the focal length field. Let's solve the camera. I'd say this turned out pretty well. Overall, we can see a straightforward camera movement and a reasonably flat wall. Not perfectly flat, of course, but it's starting to resemble one. Let's apply the result and see what we've got. Well, I'd say it's not too bad. The points are mostly holding their positions, but since we still haven't defined the distortion parameters, we can't properly composite anything into this shot. We've got a solid base track to work from. Even though we've technically got a result, it's important to remember, we know it's still wrong. This is one of those situations where you shouldn't rely solely on what the software tells you, even if it says everything is great. If distortion hasn't been accounted for, you can't blindly trust the outcome. Let's move on. Time to dig into the distortion parameters. We can even just manually tweak the distortion knob and roughly see that the value is somewhere around 0.5. But it's clear that in this range the wall starts to look the way we remember it in real life. Now let's add this parameter to the adjustment list so the software can automatically calculate its optimal value. Let's add the lens distortion parameter to the calculation while keeping the focal length. We'll reset the previous graph and start an adjustment for both parameters, focal length and, for example, distortion parameter 1. We can already see that the values are being adjusted in 2 dimensions. The current error is 0.13. Once we start adjusting 3 parameters, the graph will become a sort of 3D cube. But since we're again hitting the edge of the range, it makes sense to run the calculation once more. This means the lowest error lies at the boundary of the current range, and if we extend it further, we might get an even lower error. Let's switch the distortion parameter 1 range to fine, which will give us a tighter interval, for example from 0.45 to 0.55. Why not? Let's try. Let's see what kind of solve we'll get with these parameters. Let's solve the camera. Oh, we can see that the wall is almost perfectly straight. and the camera's movement trajectory also looks smooth. Overall, this is close to what we were aiming for. This falls somewhat into the area of parameter fitting, and it's important to understand. The more known data we have beforehand, and the fewer parameters we adjust manually, the closer to reality the result will be. That's why, ideally, distortion shouldn't be estimated through fitting, but captured using distortion grids, specifically shot with the lens in question. This is especially important when dealing with complex distortions, such as those from anamorphic lenses, which are nearly impossible to accurately reconstruct just by tweaking parameters. In our case, however, it's a simple spherical distortion.